Okay, in parts A and B of this question, give your answer to 4 decimal places. Assume 6.7% of the population of people in Ireland have diabetes. For particular, this is one of these false positives. Classic standard question. Really too innovative or imaginative in this exam. This is boring. Ah, so boring. All right. However, probably that's someone who does not have diabetes. Okay, it's all in the. I think it's all in the table here. Just complete the table. Blah blah blah. 4 decimal places, I believe, is what we need to be doing. So that is 0.933. That is 0.922. 0.933 times 0.078. So that's 0.0728. 0.933 times 0.922. 0.8602. 0.8602 plus 0.0728 plus 0.0663, and then minus the 1 away. So that's 0.0007. Okay, so good. Now I can work out this number as 0.0663 divided by 0.067. So this number must have been 0.9896, meaning this one here must be 0.0104. Okay. Use the probabilities for the tree diagram. Find the probability that the person picked at random test positive for diabetes. 0.0663. The person picked at random test positive for diabetes using this test. Oh, there's 2 positives. Sorry, forgot to add on 0.0728. 728. 0.1391. The person picked at random test positive for diabetes using this test. Find the probability that they actually have diabetes. So the probability that they have diabetes, given that they tested positive, is the probability of diabetes and positive over probability of positive. Diabetes and positive is 0.0663 over positive is 0.1391. That is 0.4766. 5 people are picked at random from the people in Ireland. Assume that 6.7% of them have diabetes. Work out the probability that 2 or more of these people have diabetes. So probability of 2 or more is equal to 1 minus the probability of 0 or 1, which is 1 minus 5. Okay, none of them have diabetes. Sorry, 0 of them have none of them have diabetes. So 1 minus 0.067. So that is 0.933 power 5. 2 or more have diabetes. The opposite of that is 1 minus 1 or fewer. So this is, they're all diabetes free. and then one of them has diabetes. So that's 5, choose one, which is just 5 actually. No need for the C here. And then one of them with diabetes, 4 of them free of diabetes, and one of them with diabetes. Type this in right. Hopefully that's right. Yeah, it should be a very small probability. Only 6%, 7% of people have diabetes, so it would be unlikely in a group of 5 to even have one of them. So 2 or more, yeah, that should be small. 20 people take part in a clinical trial. 10 of them will be picked for group A, the remaining 10 group B. How many different combinations of 10 people can be picked for group A? Is this just 20C10? 20 people take part in a trial and you choose 10 of them for A. So it's just 20C10, I think. 1, 8, 4, 7, 5, 6. No tricks. 10 of them would be picked to be in group A. The remaining 10 will go into group B. How many different combinations? 10 people are picked and put into group A. Each person in group A is now paired with a person in group B, making 10 pairs. How many different sets of 10 pairs can be made? Okay, now that's different. That's different. That is different. That is 10 factorial, maybe. 10 people are picked and put into group A. So you could have person A, B, C, D, E, and Barry, Charlie, F, G, H, I, J. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 possibilities of pairing off with Anne from group B with Anne in group A. 9 here, 8 here, etc. So I think it's just 10 factorial. I think. 10 people are picked and put in group A. Each person in group A is now paired with a person in group B, making 10 pairs. I think it's 10 factorial. In a different clinical trial, 24 people are split into 2 groups. 8 people are in group X, 16 people are in group Y. Each person in group X is paired with 2 people in group Y, so that everyone in group Y is in exactly one of these pairings. How many different sets of such pairings can be made? Give your answer in that form. Right. There's 8 people in group X and 16 in group Y. Each person in group X is paired with 2 people. The only thing I'm not sure here is the tense. 10 people are picked and put in group A. So we're just choosing with B here. In a different clinical trial, 24 people are split into 2 groups X and Y. 8 are in group X and 16 are in Y. So we know that there's 8 in X and 16 in Y. Each person in group X is paired with 2 people in Y, so that everyone in group Y is in exactly one of these pairings. How many different? Okay, so A, B, C, D, E, F, G, H. 1, 2, 3, 4, 5, 6, 7, 8. So when it comes to A, you're choosing 2 here. So you have a choice of 16 times 15. But are the pairs unordered? Or ordered? I mean, it looks, it really looks like it should just be 16 factorial. Because then this one here will be 14 times 13, etc. I really, really think it's 16 factorial. That seems so similar to the previous one. Makes me wonder what the catch is. Ah, what am I missing here? It can't possibly be the same as the previous one. I guess they want to know how many different sets of such parents can be made. What does that mean? How many different sets of such parents can be made? Each person in group X is paired with two people in group Y, so that everyone in group Y isn't exactly one of these parents. Each person in group X is paired with two people in group Y, so that everyone in group Y is in exactly one of these pairings. How many different sets of such parents can be made? The parents are between Y. They're not so concerned about attaching it to someone in X. So I'd have to divide it by 10 factorial, I think, which makes sense because that was the previous answer. But the problem is that's not really a big number. But I think that's perhaps trying to trick you because I think a lot of people think they got that answer right by getting 10 to the 13. In how many different sets? So each of these is a set. And how many different sets of such parents can be made? Hmm. Or do I multiply by 10 factorial? Ah, the problem is the English here is really confusing me. So I actually don't know. It's like, could be 16 factorial. Um, if you're attaching to an x, then hang on. So okay, the way I'm seeing it here, like you can have like a card here with two people on it, and a card here with two people on it, and a card here with two people on it. So that would be 16 factorial. But if you have these cards attached to a person as well in X, so these are all people in Y, and they're pairs, like and they're not attached. Or you could attach them to people in X, like this pair goes with the first person in X, and this pair goes with a person in X, and this one goes to person in X. So that one there would be 16 uh, factorial times 10 factorial. So is it 7.59 times 10 to the 19? Or is it 2.092 times 10 to the 13? How many different sets of such parents can be made? In a clinical trial, each person in group X is paired with two people in group Y. So I think it's this one here. You have 16 people. If you think about it, you have a list of 16 people which you can rearrange. And then you have a list of 10 people. No, hang on. But I don't want... Okay, hang on. Maybe it's this one now when I think about it. Because you don't want to stumble across the same parent again. Ooh. 16 people. Yeah, I've got a list of 16 people. I can just jumble this up and attach it to a list of 8. Oh, why do you keep saying 10 actually? It's 8 people. All right. I think I have it now. I hope. I was distracted as the previous question as in something to help me. Okay, so think about it like this. I've got 16, this is Y, and it's got 16 people. Let's say to Anne down to whoever, Bob. And then you've got X, which is 8 people, then 8 and that. So whoever's the first one here gets paired off with the top 2 in that list, and whoever is here gets paired off with the 2 in this list. So you can reproduce what's happening here by just shuffling these around. So I'm going back. I just think it's 16 factorial now. 2.092 times 10 to the 13. But I'm giving up. I'm not sure.